Okay, let's do it the German way. So since it's 5 p.m., let's start. I'm still letting people in, but that's gonna happen. So, okay, guys, first of all, thanks for joining in. I know that most of you guys are in Europe, so it might be a bit late. I'm gonna do a short introduction. I wanna thank you for being here again. This is like our second edition of this IOTA Argentina virtual meetups during the quarantine. As you know, today we will have Eric Hope. Eric Hope is going to be talking about the state of Qubic. And next week we will have Darcy Camargo. He's a part of the IOTA research team, and he will be talking about CoreSci. So the idea is to keep the day. We will try to do it on Thursdays, and also the time. I know it's a bit late for you guys, but here in Argentina it's actually pretty early. Many people is not available to attend because they are still working. So I think that's all. Oh no, wait. Regarding the questions, Eric is gonna do the presentation, and I'm gonna be using the chat to collect the questions you might have, so we don't interrupt him. And when he finishes, I'm gonna start reading the questions one by one. Okay? If it gets too long and I cannot cover all the questions, I will provide Eric with the questions, and he will be able to answer later, maybe tomorrow. So I think that's all, Eric. Whenever you want, just start.
Yeah, sure. Well, first of all, thank you, Carpincho, for inviting me. It's about time to give an update about the state of Qubic. Actually, there is a document underway. We're finalizing some little bits here and there, but it should be out pretty soon. So that's underway. But yeah, you're going to kind of get the scoop on that document, because I'm pretty much going to talk about the things that document specifies. So let's just get started. We have, here's an overview of what I'm going to be talking about. I'm going to touch on the history in a very brief way. Then we're going to be talking about the Qubic subsystems. The next thing will be the language QUPLA and the virtual machine Abra. Then we're talking a little bit about the ternary encoding. Then the Abra operations that we have. We talked a bit about the FPGA proof of concept that we delivered a little while ago. And then we'll talk about the early lessons from the proof of concept. And yeah, that should pretty much conclude everything. So, starting with the history, Qubic has been over 2 years in the making. I started in 2018. I think I joined in March with the IOTA Foundation, and immediately got handed the Qubic project. At that time, the first half of 2018, we were mainly in the conceptualization phase. That meant, yeah, thinking up what could it do, what should it do, how are we going to do it, and especially the focus at that time was how is it going to interact with Tangle, because it needs a messaging system to kind of create an audit trail of everything that's happening on the Tangle, and that should be secure and trusted and decentralized and everything else that you expect from a blockchain. So at that time it was Paul Handy and Sam Reed that together, the three of us, tried to get some information out of CFB, which was as usual very difficult, and turn that into some idea of what it was we were building. That took quite a few months. In the meantime, we had the release of the video and the hyping up of the stuff, but that was all a bit premature, actually, as far as I'm concerned. because yeah, we were just getting started and it was already clear that it was going to be a multi-year project. So first we got an idea of how we were going to set up the messaging. Over time, that has changed considerably. It only has certain concepts left of the original vision, but it's closer to getting somewhere now, thanks to Ivaldas, who you guys saw last week, who spoke about that at length. So I'm not going to dive too deep into the whole messaging layer, just mentioning it as a part of the project. In the second half of 2018, we switched to designing the actually underlying virtual machine we called Abra. Initially, it was set up as a language, and that language turned out to be, on one hand, very efficient and minimalistic. On the other hand, it turned out to be very hard to program in. As a proof of concept, I built a few mathematical libraries that could allow us to do ternary math in Abra, and the first version of an interpreter that could interpret the Abra language was built, and we were on our way to coming up with a first proof of concept. But then by the end of 2018, there was a decision made, mostly by CFB, that we needed to shake things up and that it wasn't going fast enough. So we split up the teams and turned it into the Alpha and the Omega teams, where the Omega teams were mainly doing garage style development and were going to be mostly single people working on an aspect of IOTA and coming up with stuff as fast as possible. That meant that most of the team got Shanghaied for the Omega project, and so I was left pretty much alone, and I decided to focus on the language aspect, because one thing that was clear, the difficulty with Abra, with programming in Abra, it was way too hard to actually make something useful out of it. So that's when I focused on designing a higher level language that could create Abra, and that became QUPLA, the Qubic programming language. I built the interpreter for that and an emulator, and made sure that it could generate the Abra code and even could run the Abra code in an emulator. And that all worked nice and fine. And then by the end of the first half of 2019, the Omega project was stopped. And we had a lot of loose ends, a shitload of loose ends. And it was a mess. Essentially, it needed cleaning up. It needed a clear vision, and I was asked to provide that vision, because CFB had pretty much said that he was going to no longer be involved. So that was when I started spending a lot of time on massaging all the projects into a single coherent thing, together with a few other people. That was also the time where we started the B development, the Rust development, things like that. And while doing that, well, my involvement with Qubic was at a low, but we had already built a hardware team. So my focus with respect to Qubic was mostly trying to keep the hardware team going. And so they started designing the circuitry for FPGA and testing with that, etc. and that was most of the second half of 2019. And that culminated in early 2020 in a proof of concept. Of course, that was a bit interrupted by the whole hoopla around the hack that happened around that time, and it was a bit snowed under together with some other interesting news. Yeah, we managed to get it out. It's available in the repository at the moment, and there will be a link to the documentation in the repository in the article that I will be writing or will be finishing this week. So that's essentially pretty much the history. Also in 2019, second half is when Ivaldas came aboard, and he started looking at the whole messaging layer again, and we had a lot of interaction about that. And we simplified it in an enormous way, because we already saw that there was going to be a lot of overhead in messaging, and that was not that the Tangle could not handle it, but it would mean that the decision-making process for the assemblies would be very, very, very slow, because everybody would have needed to wait for messages to show up on the Tangle. And we decided to take that all offline and have an off-Tangle conversation between the parties to speed things up. And yeah, Ivaldas is still working on that. Now that we have delivered the proof of concept for FPGA, my focus will be on helping Ivaldas. And so that's essentially what I'm working on now. I'm currently quickly learning Go, because that works on the Go Shimmer platform. And so far, I've mostly been doing Java. So that's some work that I'm doing at the moment is learning Go, and I expect to be starting helping out with Ivaldas somewhere next week after my document is out. That's the history for now. So let's talk a little bit about the Qubic subsystem. During the building of Qubic, it became very clear that Qubic is actually a mishmash of two big projects. One is the messaging and consensus layer, the thing that Ivaldas talked about last week, and that governs the assemblies. I don't know, the names have changed a bit. The group of nodes that do the running of the code, and that will come to consensus and come to a quorum and then register that on the Tangle. That whole process has been covered last week. Then there's a second subsystem, and that is the Abra virtual machine. And the way those two work together is something that I would like to show a little bit. Let me see for the whiteboard to be able to. So imagine there's the way it works with Qubic is that we get some external trigger. Here's the trigger. Oh, you have to get used to a pad. This is a lightning thing trigger, and that returns into some data. The data needs to be processed by the messaging system. Essentially, every node will run code that processes that data. The code is present on the Tangle. It has been on the Tangle somewhere before that code. And so every node, here's a node, every node will take the code, and it will take the data, and then it processes it somehow, and then out comes new data, called a result. And that gets registered on the Tangle. So we have the code, the data that is input, and the result data. Those are all registered on the Tangle, and they form an audit trail so that everybody can verify that, if necessary, that the results are correct. So we don't only have to trust the nodes or the entire quorum to be correct, because everybody that wants to can take the code, take the data, and produce the result, and should be able to verify that the result is identical. So that is essentially the process in the messaging layer. Messaging layer. Now we have the processing itself. So the node only accepts the data that comes in, and it kind of throws it over the wall to the processor. The processor then actually does the actual execution of the processor of the data, and then goes back to the node with the result, and then the node does all kinds of magic with that result, and finally it gets as a result in the Tangle. This processor is essentially completely independent from the messaging layer. So this is a virtual machine. Almost readable. Virtual machine that takes this code and runs it in that virtual machine. Essentially, there is no good reason why this processor can't be anything. The messaging layer and the processor, there is literally a dividing line. The node doesn't care where the data goes as long as it gets results back. And the processor doesn't care where the result comes from, and it just sends the output of whatever it processed. And the line in between is what we call the Qubic computation model. That's where the magic happens. And don't know whether anybody heard of EEE, Environment Entity Effect, but essentially the node will turn this into an effect that gets sent to the Qubic computation model. The Qubic computation model passes it on to the processor passes it back as an effect to the computation model, and then the computation model knows how to send it back to the node. So this is essentially an event processing system that lies in between and ties them together. The decoupling is maximal, and that means that it's like separate components that can be completely replaced. And we're actually making use of that. Right now, with the new version of the messaging system, Evaldas is initially going to use WebAssembly as a virtual machine. So it's a different kind of code, not exactly what we normally have is the Abra. Oh, now I'm just outside. Abra code that is being processed by the Abra virtual machine. But if you have WebAssembly code, then you would run it with the WebAssembly virtual machine, and you would still get the same results. So that's in short how we have set it up. It allows for very flexible components interaction, and we can exchange components, and we're literally open in the future for any kind of language. Why then do we have a virtual machine that we built ourselves? Well, that's because with IOTA, we're interested mainly in one thing, and that's the Internet of Things. A WebAssembly is kind of a big thing. IoT devices have little resources, little power, little memory. So we built a virtual machine that is very minimalistic and can still process stuff and can still participate as a virtual machine in the whole messaging system. So that's essentially why there is a separation. Apart from that, every virtual machine needs to follow certain constraints. For example, you cannot run a program that has an endless loop, because then the node that would execute it would simply hang and there would never a result be produced. What we do is that we have a virtual machine that makes sure that endless loops are impossible. It's simply not part of the runtime model that limits the amount of processing, and thereby we always know when the node starts a function, how long that function will run. And not only that, but because there are no loops and such, it's very easy to analyze the code for correctness. So those are a few constraints that we use, and that if we're going to use a different virtual machine, need to be taken into account. So that is actually part of what I will be doing when I'm working with Ivaldas, is looking at the virtual machine part for WebAssembly and see how we can make sure that code doesn't run away and that everything works the way we want it to work. Okay, let's see. That's pretty much the subsystems and how they fit together. Then we have the languages that and the virtual machine that have been developed. So what we did over time, and I touched on that in the history, is we created the Abra language. That language is an intermediate language. It's very similar to an assembly language for a processor, but it's such that we actually defined our own processor, one with very limited instruction set, yet enough instructions to be able to do complex processing. So then the next step became make that usable. And since the Abra virtual machine is running on TRID code, TRID code is actually normally if you have virtual machines like, for example, with Java or with the Microsoft compilers, those virtual machines generate binary code, bit code, you often call that. Well, we generate trinary code. We encode it as trinary because, well, due to historical reasons, everything in IOTA is trinary, and it is encoded already as trinary code on the Tangle. So the QUPLA language can be compiled into Abra, and then the Abra can be used to generate TRID code, and that TRID code can be posted on the Tangle. And then the TRID code can be loaded into the Abra emulator and then can be executed. And it means that first data will have to be presented, and then the Qubic computation model will make sure that the correct function gets called with that data. Then the virtual machine executes it, and then it returns the results. So we built the QUPLA language, and to test whether that worked, we built a QUPLA interpreter. This literally takes the statements that the language is built of, builds a syntax tree, the way it's called, and then it can actually run that syntax tree it's also kind of an emulator. It interprets the statements one by one and can execute them, and in that fashion it can execute the program. Then to test whether or not what we built was usable, we needed a library of code. So I created a large library that contained all kinds of math libraries or math functions. So it can, you have to start at the beginning, right? So we had to learn, we had to teach QUPLA how to add, how to subtract, how to multiply, how to divide, what a floating point is, how to do floating point add, floating point divide, floating point multiply, floating point subtraction, and all kinds of other stuff. So that library was created in such a way that we made use of an extra feature we added to the QUPLA language, which was a test statement. And that meant that this entire library could contain test commands that can be executed by the QUPLA language and then can be used to verify that the results are the results that you expect. It's literally the basis of software development is unit testing. Well, this language has unit testing built in. So we ran all the math libraries through some hoops, and once we had everything working perfectly, that's when we started generating Abra. And the way we did that is we executed the QUPLA syntax tree in a different way, and instead of running it as code, we now had it emit a syntax tree for Abra, and that allowed us to do the same thing over again. We could use the same tests and everything to test whether the Abra emulator was working correctly. So the moment all the tests were running correctly, the Abra emulator had proven that it was coded correctly. Then the next step would be generating thread code. And the thread code generator, again, it takes the Abra syntax tree, and instead of executing it, it generates code from that tree. And then came the big test, because we created some code that could read back the thread code and generate an Abra syntax tree from it. And then you can execute it again, which means that that same test set that we had already used for the QUPLA language and for the Abra emulator, we could now use the same test to see if the thread code generation and the thread code readback was working correctly. So that was a 3-in-1 win, where we only had to write test code once, and then it was a matter of building stuff. Finally, we created an HDL generator for FPGA. HDL is the language, in this case it was Verilog, which is the language that we used for the FPGA. So from the QUPLA or from the Abra syntax tree, both, we can generate Verilog code for FPGA that can then be converted into circuitry. That was our first working implementation that went really close to where we wanted to go with the FPGA. Okay, next slide. A little side jump. Why do we have ternary code? The thing is, in the Abra model, the execution model is a data flow model. Data flow is very specific. Let me get back to the whiteboard. So normally we have in a computer, we have a bit. This is a bit. And a bit can be 0 or it can be 1. That's the basic information unit in most computers. In our data flow model, we have an extra thing that we need. And the only way to encode that is with a second bit. So this is the data bit. And this is the bit that indicates whether or not data is present. So we need to be able to tell it's present. So you would set it to 1 to indicate, yes, there is data. But then you need a second bit to show what the data is. Or you set it to 0, and then we don't care what the data is because it indicates that there is no data. So this is what we call the null bit. And that means that for every information bit in the data flow model, we use 2 bits. The thing is, with 2 bits, you can encode the values 0, 0, 0, 1, 1, 0, and 1, 1. That is 4 different states, but we only use here 0, 1, and 0 as states because they're mutually exclusive. Either it is null or it is not null, and then it's 0 or 1. So you could say that the 3 possible values here are 0, 1, and 0 for the information. We're working on a binary system. We use the standard binary components for FPGA and the standard technology that we have at the moment. So what happens is we have 4 states that we can use, right? We can say this is 1, this is 0, and this is 0, for example. But that means we have 1 left. So what we did is we go with ternary encoding. We still have our null, our 1, and our 0. And now we have -1. This means that we encode 3 states for data. With 3 states, you are encoding more compact, right? We would have used 2 bits anyway. So why not use that final state to encode a final value? Because now, let's say that you have a value that is encoded in a number of bits. And, well, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, right? And that is some kind of value. We have 2, 4, 6, 8, 10 bits here. If we want to encode this in ternary, because ternary encoding is denser, we only need less trits. So that would be like 0, 1, minus, minus, 0, minus, and 1, for example, right? And that would then only be 2, 4, 6, 7 bits. So that means that we can encode way denser when we encode it as trinary values, because we use for every information unit, we use the same amount of bits. This is 2 bits, this is 2 bits, this is 2 bits, this is 2 bits, right? So essentially these are 20 bits. It's 10 bits of information encoded in 20 bits. And this is 14 bits of 7 trits of information encoded in 14 bits. So that gives us, on average, about a 50% advantage in the amount of data that we can encode. Binary takes 50% more space about than trinary for the same length of data encoding. So that was a very obvious optimization that we could make to get to more efficiency. There's an additional benefit here because in essence, the data flow model works with all those separate bits at the lowest level because we are working with circuitry in the Internet of Things. We're not working with a standard programming CPU, but all the instructions that Abra gives us are instantiated in circuitry, and at the lowest level, they work on these entities, on these information units. That means that, for example, if you do an addition, normally when you add, for example, 1, 2, 3 plus 7, 9, 8, right? When you add, you have 3 plus 8 is 11, and you get a carry to the next digit. 9 plus 2 is 11, plus 1 is 12, and we have another carry. And then we have 1, 2, 9, right? So this is how you add normally. The same way happens in binary and trinary, that when you add a whole string of them together, you have binary digits or trinary digits, you get carries. Here, in binary, we therefore have 50% more carries than we have in trinary. And since every carry depends on the previous calculation, we first need to calculate this to be able to see if there is a carry, and then we can calculate this and see if there's a carry. So it's a sequential operation. That means that here we have 10 operations, and here we only have 7 operations. So it's about 50% faster than the equivalent binary. And that gets even worse. I don't know if you still remember from high school what happens when you multiply 1, 2 times 3, 4, right? You take 4 times 1, and 4 times 2, and 3 times 2, and 3 times 1, and then you add, and then you get 408. So you have a cross multiplication for all the digits. And that means that if this thing becomes 10 digits and this thing becomes 10 digits, then you have 10 times 10 multiplications that you have to do. And that then results in a shitload of additions, and all those additions have that same problem that we just saw, where the carry needs to be transferred. So in this case, with a multiplication, you get that it's not 50% faster, but normally it's a factor 1.5, but because it's now times, you get 1.5 times 1.5 or 2.25 times faster. So you see how that can quickly escalate into a really big win within the same model, because literally nothing has changed. The only thing is that we now use this original unused bit or bit combination to encode values, and for the rest, the code and the circuitry and everything is exactly the same. So this is how we already knew up front that ternary encoding would be more efficient space-wise. It takes less space to encode a number, and in execution speed, because you have to do less. And that's very evident from these kinds of mental exercises. You don't even need the actual implementation yet to be able to see that this is more efficient. So that's why we went to ternary encoding. We have come up with 2B and 3B encoding. The 2B encoding is literally this one. And it's 2B encoding because it uses 2 bits. We also have a 3B encoding, and that uses actually 3 bits. It may seem that this is more wasteful, but this has the advantage that there is never more than 1 bit at a time present if you have data present. In this case, if you have 1, 1, in this case, there is a moment where the circuitry hasn't stabilized yet, and you're not sure whether it is 1, 0, 0, 1, or if it will eventually stabilize into 1, 1. Here you don't have that problem. The moment a 1 occurs, you know you have your data. So it allows you to do some trickery with circuitry at the lowest level to be more efficient at the cost of one extra bit. And that's a trade-off. We're always using zeros as the values for null. And that is because null is the default state for our code. Everywhere in our code, we try to go to null as fast as possible. Actually, we start out, everything is null, and only those places, those paths in the circuitry that get a value will have to switch. And in CPUs, switching is what is costing energy. If you don't have to switch, you don't have to spend energy. So this is why it's important for us to get everything to null as fast as possible. And since null is encoded as zeros, it uses zero energy. That's the idea, the basic idea. Let's see, where was I? So I already touched on why it's more efficient. And then we have the obvious question. You are using binary hardware, but why not use real ternary hardware? Well, real ternary hardware, you would have a TRIT. And a TRIT can have 3 different states. minus, 0, and plus, or often also minus, 0, and 1. Like I indicate here, minus 1 is the extra value. In this case, we would have hardware that actually can produce 3 different states instead of 2 different states. This hardware is currently not available. A lot of people have tried, but it has a lot of problems and disadvantages compared to pure binary hardware. It's simply way more difficult to create hardware that does switching like that. There are certain other items where it could work. That's, for example, if you would go to Li-Fi, then you get positive, negative spin and 0 spin, for example. But that goes too deep for this discussion. But anyway, if you would have TRITs, then this data model becomes actually quite funny, because as we saw earlier, for the data model to work, our data flow model, we need a null value, we need a 1 value, and we need a 0 value. Well, guess what? Here we have a 0 value, here we have a 1 value, and we can use this one as our null value. That means that on actual ternary hardware, it's probably more efficient to encode it as binary data, right? We encode zeros and ones. We don't have the minus 1 value anymore, because that one is now taken up by null. So we can create the exact same data flow model, but now we only need 1 TRIT, and that TRIT has 1 state that will actually encode the absence of data. And the other 2 states are used for information. So in this case, we would need, for encoding 10 bits, we would need 10 TRITs. So that is a side effect. It's very weird. On binary, it's more efficient to encode as trinary, and on trinary, it's more efficient to encode as binary. Very, very weird side effect, but yeah. Actually, you could go even further, because you could say we can use 2 TRITs the way we use 2 bits, and then we have 1 state that is null, and that gives us 8 states. So you would encode bytes essentially in 2 TRITs, and the absence indicator would also still be there. So again, you would be encoding something that works more binary than actually ternary. So that is, in short, the whole ternary discussion. Let's see. Okay, so our Abra model, it has only 5 instructions. Those instructions are concatenation of thread vectors. A thread vector is data. You saw that on the other page. Let's see, where is it? This is a thread vector, right? Here I have 7 threads. So the thread vector is 7 threads long and it encodes a value internally. So operations you will need if you work with this model is you want to be able to concatenate thread vectors together into a bigger vector, or you want to be able to slice a thread vector and take a sub-vector out of it. Essentially, we use a lot of divide and conquer techniques in our library, our code library. You, for example, get a 9-thread input value that needs to be added. And what we do is we split it up, we slice it in 3 3-thread vectors that each get sent to an adder for 3 threads. And those in turn will slice each 3-thread slice into 1-thread slices, and then it will be able to add a single thread. And that's the lowest level. And then coming back up out of the calculation, the results are being concatenated together into a 3-thread vectors, 3 3-thread vectors, and then the single result is a 9-thread vector, right? So this is, these operators are pretty much used for grouping threads in such a way that the programming language knows which belong together and how to use them. Then we have a call function. Every piece of code in Abra is a function, and a function can call another function. So, like I said earlier, the 3-thread or the 9-thread add function calls the 3-thread add function 3 times with 3 different slices of the input values. And the 3-thread calls the 1-thread version with 3 different slices of 1 thread. So call function is essentially very similar to what happens in a normal CPU when you do a call, but it has a few twists, and I'll go a little deeper into that later. Then we have the lookup table, which is the most basic block in Abra. It's essentially the only, pretty much the only instruction. It takes a few threads for input, looks up a corresponding value for that combination in a lookup table, and then it will return the value that it finds in the lookup table. Funny thing is that with lookup tables, you can pretty much do anything. We have a lookup table for 1-thread multiplication, for example. All the combinations that you can have for input give a certain output. Same thing for adding, and you can even have adding and including the carry by taking 2 lookup tables, one to add the bits and one to generate the carry thread. And so these lookup tables are yeah, pretty much amazing. They can do everything that you need to do in a programming language. The only thing that you need, and that's something that we use by having a null encoding. The null encoding, the absence of data is very important because you want somehow to indicate which data flow path contains the data and all the others don't contain data, because everything happens in parallel in Abra. It's essentially circuitry, so it's maximally parallelized. Every single thing that can be parallelized is parallelized, and only the things that depend on the output of a previous lookup are sequential. Everything else is in parallel. So that means, for example, in the multiplication, if you multiply those digits, that cross multiplication, funny enough, it's completely independent. Each multiplication is independent. So if you have 10 by 10 trits that you want to multiply, that gives you 100 multiplications, but they can be all done in a single, you could call it clock cycle, because they all happen at the same time. Then you get a number of results that need to be added, and those are sequential. So first they depend on the multiplication, and then you go to the addition phase of the multiplication, and then you have to do them one by one, and those are sequential, and then you get a result, right? So you have to do that in sequence. Then we have finally a merge operation, and a merge operation is an operation that's essentially also a lookup table, but it's a very special one because this one expects that the inputs only one value of the 3 input values has data. The others have only the absence of data and are null. That means that it's essentially what do you call it? It's called a Y. I mean, I believe if you have water, let me just draw it. That's why I have a whiteboard. So you probably all know how a Y works. This is 3 input flows of water or chemicals or whatnot, and here's the output flow. Well, with our merge, only one at the same time is allowed to flow, and then the output is that one. So let's assume these are 3 different chemicals, and whenever 2 chemicals mix, you get a big explosion. So you don't want that. So you only allow 1 chemical at a time to flow through, and thereby you select a path through the code that produces the result, and the other parts don't produce the result. It's very important for Abra because you essentially get some lookups, and lookups can depend on other lookups. So let's, for example, let's have 3 of them depend on the first lookup. They all do a different kind of lookup, and then those together go into a merge, and we get one output again. So where in normal computer code you have an if then else, you get if some kind of condition, then execute this. Otherwise, if some condition and execute this, otherwise execute this. In this case, we execute all 3, but 2 of them will become null, and only 1 of them actually has data and can flow through. This is being assured by the QUPLA compiler. It makes sure that there's never a path that can be non-null, or multiple paths that are non-null, because then you would get the big explosion. So those, this is essentially also a lookup operation, but it takes slightly different kind of input table to code it correctly. Okay, those are the Abra operations. Then we use that to build a proof of concept on FPGA. So our friend Jonathan in the FPGA team, with the aid of Thomas and come on. Okay, I'm very ashamed. Donald, yeah. I'm so deep in my talk that I can't remember names at the moment. Sorry about that. Jonathan is a very experienced FPGA programmer, and he designed a circuitry for the FPGA that allows us to run the Abra code. So it's essentially a virtual machine. The way I built the emulator on the PC that can run the code, he built an emulator on FPGA. So it's literally, we're using a programmable device. FPGA is a field programmable gate array. It has a number of circuitry blocks, and you can program them and combine them together so they all are connected to each other, and then data can flow through the circuitry and perform a certain function. So Jonathan programmed the FPGA to allow it to be programmed with Abra. This is one very important aspect. FPGAs are normally very different. There are all kinds of manufacturers. They use proprietary code to program them, and that means that you have to lay out the circuitry. If you have some kind of program, you have to lay out the circuitry for every type of FPGA separately. That's a very long process. Laying out circuitry is quite more difficult than a simple compilation of a program. It will essentially sometimes take a whole day or longer of running on a PC to generate the circuitry layout for an FPGA program. Excuse me. Now, imagine that you have such an FPGA program and you need to fix something. You find there's a bug in there. You go back, you fix it, and then you have to wait another day for the output to appear so that you can actually run it on an FPGA. And now you have different proprietary FPGAs, and each of them, you have to run it for an entire day to be able to actually run your program. That's, well, not only very time consuming, but it's also very costly because pretty much every proprietary FPGA is hidden behind a paywall. So if you want to develop for another FPGA, well, guess what? You get to pay again for literally the same software, only this one is then targeted towards that specific FPGA. Now here comes Qubic. What we do is we create an Abra VM. We only have to program that once, and we can then lay out the circuitry for the FPGA, which is slow, but we only have to do that once for every type of FPGA. So one day of running, and now we have the code for, well, for example, this thing here. This is the DE10 Nano. It's the FPGA board that we use for our testing. And so essentially our friend Jonathan compiles the circuitry layout for the FPGA, and then we can load that on the board, and then it functions as an Abra VM. And that means that if we want to program it, we now can program it in Abra. We can test that easily on a CPU because we have an emulator. We don't have to run it immediately on the FPGA. So that cycle of development is already really fast. But in addition, you simply load it. There is no layouting necessary, no circuitry layout necessary. You simply load it into that FPGA that runs the Abra VM, and it will run. And it will run the same on every FPGA that runs the Abra VM. So that's a huge step, and it cuts out a lot of middlemen, because we can simply provide as open source a virtual machine for pretty much every FPGA that we built once, and then everybody can program the FPGA in Abra. That's already a huge thing. This is essentially what we have created as our proof of concept. We have the Abra VM on FPGA running. It's essentially one big block of lookup tables, because once you start using Abra and you start instantiating it on the FPGA, you will literally only end up with lookups. All the grouping that happens when you do the concatenation or the slicing, and also the calling, it all gets reduced to simple wiring, because all you need to do is hook up one circuit element with another circuit element. And the grouping is more conceptual than actually necessary at the FPGA level or at the VM level. Calls are a different kind of beast. A call gets instantiated. Whiteboard. So normally you have a program call tree that looks like this. Just as an example. So this is the top of your call tree. There are instructions here, blah, 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 blah. And at some point, a call gets made. That in turn executes instructions, and there's a call being made, and there's a call being made. Then the result is being returned, executed in the instructions. It goes back up, continues here, call is being made, blah, 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 call is being made, blah, 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 blah. The return value is returned, blah, blah, blah. And so that's how you literally execute a program normally. There's one difficulty when you do that in circuitry. That is that the return value needs to go somewhere. You need to know where it goes. So what happens in practice in Abra is that a function gets instantiated, the way we call that. Let's assume that this is the same function that's being called. This is a multiplication function, for example. And this is function x, and function x gets called again here, and it has the two multiplications, right? So if we code this in a standard program, then this part is not there. You get the call to x, x will call the multiply, it will call the multiply once more, and then further down, x gets called again, which calls the multiply, and which calls the multiply again. In Abra, you can't do that because the output of circuitry needs to be connected to wherever the return value goes. So in Abra, what you get is, if there is a call, then we instantiate the function x. And since it's being called here again, we have two instances of x. So this is literally the entire code. This entire code is instantiated here. In fact, because it uses multiply twice, the x has to multiply, and this x has to multiplies it. So this is so that it's able to return the values correctly. If I zoom in on x with its multiply and its multiply, then what essentially happens is that the data flows in, through the multiplier, comes out on the other end, goes further down whatever other instructions are there, then flows into the next multiplier, and what comes out here, and here's the output. Actually, here's the input. It's not like coming in from above, like you would expect, but coming in from the side, and it's just a sequential data flow. Thereby, you get a second one here. So here we have the X with the two multiplies, and the data flows through like that. And that in turn has the overarching function. That's this one. So as you can see, in a syntax tree, you only have one multiplication function and one X function. Here we have two X functions and we have four M functions. So that is how different programming an FPGA is, because you're using circuitry. Now we have an FPGA, that DE10 Nano that we're using, that is pretty limited size-wise. It doesn't have that much programmable circuitry. And because you program the circuitry to create programmable circuitry, you end up with even less programmable circuitry. And that means we currently, in our proof of concept, even though it works, we can only have pretty small functions that contain about 500, 600, 700 instructions maximum, or we run out of FPGA. If we want to do bigger ones, then we will need to buy a much more expensive FPGA. This board costs about $150. There are FPGAs out there that cost tens of thousands of dollars and have lots and lots more instructions. I hope I am, you guys can hear me, because I hear the...
Yeah, we can, Eric.
Okay, because let me...
Yeah, the things that everyone
one second. Okay. I need to tell them not to use the microwave, because that kills the internet here. 1 second.
Okay, no problem.
Sorry about that. Those kids don't understand that. Okay, let's continue. So the proof of concept is working. We can use it limited, and yeah, obviously the next step that we're looking at that will be interesting is creating our own FPGA essentially, but it will be an ASIC. An ASIC is a specific instantiation of functionality that you would normally put on an FPGA, but now you hardwire it, so you no longer have a programmable FPGA, but you create circuitry directly that does the exact same thing, and that's what we call an ASIC. What's the acronym again? Slips my mind, sorry. But what we would do is we would create the Abra VM on an ASIC. That means that that one extra level that we now have in the FPGA, where we have a programmable system to implement a programmable system on top, we would now directly create our programmable system, and that would lose all the overhead that you have of the underlying FPGA system. That means that in that chip that you would create, you have much more circuitry real estate available, and so the amount of code that we could load in such an ASIC is much, much more. Essentially, that is only an intermediate step. It could be that for IoT devices, we would, by using such a thing, literally bypass the entire FPGA market if we create an open source ASIC. That's how important this development is. We would open source the ASIC, no proprietary code there, and then anybody can create those ASICs or just buy them and then have run Abra programs on that. And then finally, which is the last step, and that one is where we are looking for IoT devices. We would directly generate circuitry in an ASIC from Abra. So we would no longer have the virtual machine running on the ASIC, but we would have the Abra code directly running. That means that you cannot change it. It's not programmable, but a lot of applications in the IoT arena are one shot anyway. So for example, let's assume you would drop temperature sensors over the rainforest, and these can mesh network together, and you can use them to gather data about the temperature everywhere in the rainforest. Well, once you drop them, you have no idea where they are, and you're not going to upgrade them anymore, right? So first you create the code on an FPGA or on an ASIC that can run the Abra virtual machine. And once it's okay, you could create an ASIC, a very cheap chipset specifically for that purpose. That could be built into those little sensors, and then you can drop the sensors, and then you can network them whatever you want. So that's the end game that we're looking at. Okay, what are the initial lessons that we learned by going through this entire process? And I'm talking now about the whole virtual machine part. The design works as intended. It's literally, it's running. We can run Abra both on a PC, in a normal CPU. You can run it on any processor, and we can run it in FPGA, and it both runs perfectly. The emulator that we built into the QUPLA code that runs Abra is now able to load a specific function. We indicate the function, and then it will load that function on the FPGA. It will talk to the FPGA, load the function on it, and then when it executes its own code, whenever it encounters a call to that function, it will ask the FPGA to execute the function. It all works flawlessly, and we've tested it with multiple different functions. We ran our entire test set against it, and again, we have no error. So it's working exactly as intended. As I indicated, the proof of concept is very limited at the moment, especially because we're using cheap FPGAs, but it was a proof of concept, of course. So we just wanted to see, can it be done? And yes, it can be done. And the next step would then probably be to go to ASIC. And that is something that we'll first need to do some analysis and research on. So there's more analysis and research needed, for sure. And then finally, that function instantiation that I was talking about, it can become a hurdle because a tree is exploding pretty quickly. If a function calls two other functions and each function calls three other functions, then those three functions get instantiated twice, and the two calling functions get both instantiated. 1 second. My battery is empty. Okay. So yeah, we need to solve the explosion of circuitry that is caused by this, and we're still looking into several. The FPGA guys think about that, and meanwhile I will be working on the smart contract side of things. Let's see, is there anything I forgot? I think that's about it. Yep.
Alrighty, thanks a lot, Eric. Amazing talk. So we do have some questions. I'm gonna read them in the order they were published. So the first one says, David estimated co-design to happen by Q1 2021. Any estimated time of arrival for Qubic? This is a when Qubic question.
Well, we have a timeline. The timeline has been delayed a bit first with the fact that we got the stupid hack, which caused our proof of concept to get delayed and my article to get delayed. And then there was the whole COVID-19 thing going on, which also has been interrupting our workflow because we were about to put our heads together for the next steps. And we now need to do all that online, and it simply works way better to be in one room with a whiteboard. So yeah, right now I'd still say look at the timeline on the roadmap website, and add a few months, add 3 months or so. The smart contract side of things, I don't remember if Ivalda said that last time, is married to co-order side, right? It's on Go Shimmer. It will not run on the standard IRI. So that's because we need a few mechanisms to be supported. We have the multiple signature that we use in that layer that needs to be implemented in the lowest layer, because we need to be able to control addresses and send funds to other addresses and such. So that's the biggest problem that we have there. And by having BLS signatures built in at the lowest level, we will be able to do that. And that's for example, one of the things where we deviate from the original idea, where we had gateways that would do the token moving. We will be able to move tokens directly on the IOTA layer. And that also means that if they implement color tokens, we can probably move any token directly on the IOTA layer without needing gateways. And that's a pretty interesting. Well, actually, the gateways would still be there because you need a gateway to get the color tokens to be loaded and to pass ownership outside of the tangle.
Okay, so let's go with the following question. What is your opinion about the switch from ternary to binary within the foundation?
It's not exactly a switch. We still have the ternary as we want to stay backward compatible as much as possible. So we're not just dropping it. It's more a switch to internally doing things binary, because the original version was encoded such that every time we needed data from the tangle, we would have to decode from trinary to binary. And if we would store something, we would have to encode from binary to trinary. And all those encoding steps, a lot of them were redundant. Sometimes you would decode the same data 20 times, right? So it makes more sense to do the decoding once. So you get the data from the tangle, you immediately decode it to binary. Internally, you only work with binary. And then the moment it needs to go back on the tangle, that's when you encode it back into ternary.
Yeah. Totally. Okay, so next question. If the data flow model between trinary hardware and binary encoding is as effective as binary hardware and trinary encoding, is there any reason to switch to trinary hardware on the long term?
I literally don't see that happening soon. Maybe if light processing becomes a thing, then I could see it happening. But for now, with the current crop of electronics, binary is everything's binary. The problems they encounter if they want to create a ternary circuitry are huge. It's very hard to have three levels. It's much easier to discern between two levels than between three levels. And the circuitry switches slower because it has to jump a larger difference in voltage if you do it with voltage differences. So I don't see it happening very fast or very easily. Actually, my best guess is that Jin also was buying.
Okay. 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 Next question. I'm trying to do it fast because I know it's
Sure.
very late for some of the guys connected. So this one says Jonathan didn't agree that non-reconfigurable cubics made sense. Well, so he has changed. Has he changed his opinion on that? Did you understand it? Because I read it as I got it from the chat, and maybe it's not.
Could you repeat the question?
Yeah.
What was the opinion?
Let me just rephrase. It says I'm gonna rephrase it. Didn't Jonathan agree that non-reconfigurable cubics make sense? And then he asked, has he changed his opinion on that? Does this make any sense to you?
Well, non-configurable qubits make sense in certain applications, of course. Like I said, if you're building sensors or such, and you can minimize everything to the limit. The thing is that there are a lot of crazy optimizations that you can do when you actually are no longer non-programmable. Because as long as you're programmable, everything needs to go through a lookup table. But once you drop out of the lookup table paradigm, you can have lookups that are simply reducing to a simple or and, or even just simple wiring. And that should enable all kinds of tricks. But the thing is, you will have to lay out that circuitry. And then you get back into the territory where the FPGAs now are and why they are so slow. The layouting is the part where you make sure that all the wires don't interfere with each other and are not too long, and the timing signals make sense and whatnot. That is what is the hard part there. And that's a very convoluted search through the solution space to get to the most optimal solution. And so I don't know what that will look like. We're nowhere near that yet. Whether it's doable is also still a question. We haven't done it yet. So it's a step-by-step process. And even though look, we get a lot of questions. Why haven't you guys done the proof of concept at the lowest level yet, right? And yeah, the simple thing is that you can breadboard all you want with separate and OR gates and whatnot, and put it all together. But once it turns into a chip in an ASIC, it behaves so differently that it's very hard to do. So we would have to create chips. And creating a chip is not something you do just offhandedly. It's a pretty big investment. I mean, once you have a chip and you know what it looks like and you can build it, then it will cost only a few cents a piece. But the initial few that you want to churn out, they're costing tens of thousands or hundreds of thousands.
Yeah.
And so, yeah, let's just wait a little bit until the token price goes up.
Okay, so I'm going to continue. For realistic workloads, would it not make sense to have a single null bit for groups? For example, bytes, words of treats, bits, instead of a null state for each bit treat? Did you understand the question?
Yeah. Well, the thing is that we want to be able to see for every bit if there is data or not, and turn it into null as fast as possible, right? Essentially, we want most of the chip to be dark, to not consume any energy. And to achieve that, it goes at the cost of an extra bit. That's too bad. If you would do a separate null bit, then you have another problem, because then null becomes a switched signal. So you turn it on or off, and data itself is on or off. So it becomes more energy that you spend that way, and less of this chip will be dark.
Okay.
It's the clever encoding that we're using that makes this thing happen.
Okay, let's move on to the next question. Which programming language is QUPLA's syntax closest to? If any, I mean. No.
I just started coding. I coded myself into a corner, saw that some things didn't work. Oh, now I need this. So let's add a template-like feature. Okay, that works. Now we need, oh, wait, we need multiple functions within a template. Okay, let's add that. And that's how it grew. Of course, I know a shitload of programming languages. I've worked with so many, and I don't know.
But you wouldn't say that you got your inspiration or part of your inspiration from some other language?
No, actually, I got most of my inspiration from the things that I'm usually fed up with in languages.
That is a good way to
avoid that at all costs.
Invent a new language, yeah.
Right? For example, the QUPLA code only needs a single reference to other QUPLA code. It doesn't matter where it is. It also doesn't matter whether it's multiple, but it only needs a single one to pull in another library. Right? It doesn't need to go through all kinds of convoluted stuff. It doesn't need a complex make because it's simply folder-based. I cut out all the difficult bullshit that most of the time I'm like, why the hell does it have to be this complex?
Okay, so we have two more questions. The next one says, since the #1 requirement for IoT is being cheap, how many LUTs do you expect to be able to place on a low-cost chip? Or when do you think you can say something about this and compare it with existing solutions?
Yeah. It depends on the size of the chip. A lookup table, it takes 27 input values and produces a single output bit. So you essentially get 54 inputs and 2 outputs. And all the circuitry to do that, which means a bunch of OR and AND ports and some stuff to be able to program it. But I'd say that if you can create a RAM that has a gigabyte or more, then I would say that a million LUTs should easily be doable. Because if you are literally making an ASIC, then there is no limitation, and you're reproducing the same circuit.
Okay, and the last one, this one just says, where do you see the biggest use for Qubic?
The biggest what?
The biggest use for Qubic.
The
What do you
biggest
think?
use.
Use, yeah.
Well, like I said, the idea was to be able to work with minuscule IoT devices and literally generate circuitry. That was the end game. Secondary is the fact that Abra can be generated by all kinds of tools. And if you look at the literature, then there is a shift towards looking at Ternary for AI and for decision making and such. Just because you can have a undecided state, you have a different way of working with AI circuits and AI programs even.
Okay.
So that might be something. And then finally, if you get all these micro programs running in the cloud and they start triggering each other, you can generate something much bigger. But what that will be and how that will evolve, we just provide the tools, right? There are certain ideas, but nothing concrete there that we actually.
Okay, so there is a lot of potential, but yeah, but first you guys gotta finish. Okay, that's all. That's all I have. I don't have more questions, so I think we have finished. So I just want to thank you again, Eric, for being here. It was an amazing presentation. Also, I want to thank all the people that connected. I know that it is late for some of you. So all these meetup will be available tomorrow in YouTube. And remember that next week we will have Darcy Camargo from the IOTA research team, and we will be discussing core design. So thanks a lot, guys, and see you next week.
Thank you, guys. Bye-bye.
Bye, Eric. Thanks a lot.